All right, hey everyone. So we're back looking at simple linear regression. Now we're gonna spend the next couple of videos talking about model assumptions. And so we've had these kind of like checks for all of the hypothesis tests and confidence intervals that we've done so far. Usually there's only been a couple, so like usually we've checked independence and we've had some sort of like sample size type condition checking either like if n times p hat is bigger than 10 and n times 1 minus p hat is bigger than 10. We had like expected counts for those chi-square tests, etc. So regression is like no exception. There's still going to be some things that we're going to have to check in order to build confidence intervals and do any sort of hypothesis tests. And so that's kind of like what the next topic is going to be. And for regression, there is, as you can see, a few more checks than usual. And so we've kind of abbreviated these assumptions LINC. And so we're going to check linearity, independence, normality, and constant variance. So the first assumption, linearity, we've actually already talked about. And so we're just assuming that the relationship between y, our response variable, and x, our explanatory variable, is linear. How we're going to do this is we're just going to check the scatter plot of y versus x, where y versus x means that y goes on the y-axis, x goes on the x-axis. You could write your own example of something that's like a violation. One example that I thought of that could be nonlinear is maybe if you plotted people's study time and your response was exam score. I'm thinking this could be nonlinear because exam score is going to be pretty low for no study time and it's going to kind of increase, but there's probably like a limit where no matter like if you keep studying or if a person keeps studying, their exam score might not continue to go up since it has to cap at 100. And so if you studied for like 1,000,000 hours, that's not going to be that different than studying for like 3. So this might be a nonlinear relationship because we see curvature. Okay, so we've already talked about that one, so that's pretty quick. Independence, we're assuming that the errors in our regression equation are independent. Again, it's kind of easiest to think about this in terms of examples. So let's go ahead and write down an example of non-independent data. The one that I could think of is like weather data. So if you graphed x as time and y as the daily high temperature, then we're just going to note that the errors are going to be correlated since today being warmer or today being warmer than usual just means that tomorrow is likely to be warmer than usual. So maybe not in Ohio, where I'm from, where people like to joke that it could be 30 degrees one day and 70 degrees the next, which is sadly true. But in most places, these errors are going to be correlated because if it's like, so right now it's late March, and if it's in the 60s in northern New York today, it's going to be likely to be warmer than usual tomorrow as well. And so the third assumption is normality. And for this assumption, we're assuming that the residuals are normally distributed. So this isn't necessarily that the response is normally distributed. It's not that the explanatory is normally distributed. It's just that the residuals are going to follow this normal distribution. To check this, we're going to check a histogram of the residuals. And this is kind of like the least important of the assumptions. And so we're just going to make a note that if our sample size is somewhat large, then this isn't super important for most topics in regression. In particular, it's not super important for all of the topics that we talk about in intro stat. So this is, if we have a large sample size, then most of the time we're pretty much good. The final assumption, I think, is the newest one. And this is constant variance. And so we'll write out what this is first, and then we'll kind of see it in action. So constant variance means that the variance of points around the regression line is constant from low values of x to high values of x. What we're going to do to check this is we're going to check something that's typically called a residual plot, which is just a plot with the residuals on the y-axis and our explanatory variable x on the x-axis. Oh, 1,000 pardons. So, what does this mean in terms of looking at this residual plot? Well, let's draw a couple of examples since this is the kind of relatively new assumption. So something where the assumption is going to hold is we would make this plot with residuals on the y-axis, x on the x-axis, and what this really means, I'm just gonna kind of draw something like that. I'll kind of keep going, and it could even be something like this over here. So what this means is that as I'm starting from the left, I'm going to make sure that the spread of these residuals doesn't drastically increase or decrease as I'm moving across the x-axis. So it starts out kind of big here. It might get like a little bit smaller and then a little bit bigger, but it's mostly like fine for this example. Something where this constant variance assumption isn't going to hold. I'm going to draw another graph with residuals on the y-axis and x on the x-axis. The most common example that you'll see where this doesn't hold is this kind of funnel-y shape pattern. And so in this example, I am starting at a small value of x, and I'm seeing that the spread of those residuals is really, really tiny because they're really clustered around that x-axis line. But as I move across, the spread's getting bigger and bigger and bigger and bigger and bigger and bigger, bigger, bigger. So this is an example where this assumption doesn't hold because the spread seems to increase as we move across the x-axis. Okay, in the next video, we'll talk a little bit more about checking these assumptions using residual plots. Using the course evaluation data set that we've been using for prediction in some of the other examples.